Thank you. So first of all, I would like to thank the organizers for giving me the opportunity to tell you a bit about our work. So this work was done in collaboration with Bo Lee when he was still a PhD student in the Hong Kong University of Science and Technology. At the moment, he's a postdoc working with me on other issues. So I'm going to focus on the function entropy in deep learning machines. The outline of my talk, so first I'm going to motivate the study of deep learning machines, highlight some successes and pitfalls. I'll then say something a bit more general about statistical mechanics of learning from examples and why the entropy in function space matters. I'll look at results of continuous and discrete weights, densely connected and sparsely connected networks. All of that will be clear when I'll talk about this. I'll present the general framework and show some results. And also show some results on correlated weights and convolutional neural networks. Then we'll do some large deviation analysis in order to look at sensitivity to perturbations and finite size effects. And more specifically, what is the impact of binarization and sparsification of deep learning machines. Binarization simply means that all of the continuous weights are reduced to plus minus 1, and sparsification is simply dilution of the weights connecting subsequent layers. And these are the publications that are related to that. Okay, so I think that undeniably, deep learning machines have managed to show some amazing engineering successes. So they managed in computer vision, speech recognition, they managed to solve an old problem that have been bothering humanities for a lifetime, which is to distinguish between cats and dogs. And on top of that, there is speech recognition, playing all these nice games like Go, Atari, and so on, composing music, creating artwork, generating fake videos, something that we've really longed for many years, and many others. But not all is well. So for instance, Google AI is an absolutely amazing tool. The only problem is that this plastic turtle is also recognized as rifle in some of these images for no good reason. I mean, Mark showed you already the panda gibbon classification and the sticker toaster sticker classification and so on, but there are other blunders as well. So the British Metropolitan Police decided to fight pedophilia, and they've devised an excellent tool to remove all images of nudity from the network. And interestingly, also all of the pictures of deserts have disappeared as well, because at the end of the day, what they've managed to identify is skin color and smoothness. So to be absolutely honest, I don't know if they've been using deep learning machines or not, but it has all the hallmarks of deep learning machines and neural networks, because you're doing something and you don't quite know what you're going to get. But they also tell us that deep learning machines is really easy, because you start from neural networks somewhat related to the behavior of neurons and so on, and you have an input layer, hidden layer, and output layer, and then you add as many layers as you wish, and everything is going to work. So if you actually look at how the record-achieving networks look like, they're nothing like that. They're very specifically and carefully crafted in order to address specific issues. There are convolutional neural networks, there are pooling, max pooling, all sorts of tricks that people have been doing, and there are, I haven't counted how many layers there are here, but this is the record-breaking deep learning machine. So the main point is we have to understand what is going on, and more than anything, we have to understand, is deeper better? Because this is not absolutely clear. There is a lot of empirical evidence. The question is why, if at all, deeper is better. I should add a health warning to my talk. This is all about random inputs, random networks, random architectures. So it's not necessarily directly related to what people are doing, because most of the data that people are working on is not random, is very sparse, very correlated, but this is the framework that we can look at. So in general, we have something like that. We have an input layer. It is connected through a set of weights to the next layer, which is connected through a set of weights to the next layer, and so on, until we get to the final layer. Layers are not necessarily of the same size, but that is absolutely fine. At the end of the day, we have an output which is some function of the input given a set of parameters, W. In most cases, we get it in supervised learning, we get training data, which simply represents a set of input and output examples. So, for instance, images of cats and dogs and the classification of cats and dogs. So there is an image function and it classifies it as cat. What we need to understand is what is the generalization ability of deep learning machines in spite of the fact that they have numerous parameters. That is an important point because we have a space of parameters that is extremely large, and somehow in spite of the flexibility, huge flexibility that we have in this space, we manage to generalize well. Another open problem is the nature of the internal representations. What is actually happening in the internal representation, and this is something that I'm not going to address in this talk at all, but it is nevertheless a very important issue. So just briefly talking about what people have been doing in this area in the 90s. So people from the statistical physics community looked at disordered systems of very large dimension and mapped them onto statistical physics frameworks. And we threw at them all the methods that we have and know. Replica analysis, cavity method, dynamical methods for online learning. And we exploited the high dimensionality of the space in order to look at all the parameters, in order to exploit the self-averaging property of many of these systems. We typically looked at typical behavior rather than the worst case scenario that people in the theoretical computer science community are looking at, which at least in the 90s gave bounds that were very far from the typical performance. All of these calculations are technically quite involved already for the single layer network, but more so for the two-layer systems, and there are very, very few works of specific architectures and training scenarios that actually could be analyzed. The input data structure and internal representations are rarely addressed. Usually you simply look at random data and you don't care much about the internal representations. So one of the scenarios that people looked at is what is called the teacher-student scenario. In the teacher-student scenario, you have two identical or non-identical systems, and one of them is producing the examples, and the other one is learning the parameters in internal structure on the basis of these examples. So they play together. What it gives us is a possibility to compare the performance of the teacher and student, and many times it also gives us a way to measure the correlation between the two. The difficulty with doing it for deep learning machines is the fact that we have many, many different parameters, recursive nonlinear mapping. We have complex hidden layers, and also all of this is constrained only by examples from the beginning, from the start and the end. To make it even more complicated, in each one of the layers, we have what is called the permutation reflection symmetry. Permutation simply means that we can swap change the order of any of the neurons or nodes in each one of the layers. Reflection simply means that we can multiply everything by -1, the input and output in a symmetric activation function. So this makes things very difficult, and The overparameterized regime is particularly challenging because of the different hidden symmetries that exist on top of that. So what we would like to focus on is what is called the function space and its entropy. It is not the energy landscape, and I want to explain the difference between the two. So let's say that we have a reference or target function, fw hat. What we would like to explore is how many functions in the vicinity, in terms of small perturbations, to this reference function will give us a good approximation. So we have possibly noisy data, we have suboptimal training methods. All of that is less important. We are not talking about the training methods. We are just trying to look at how many such functions exist for a given error. And the conjecture is that the entropy, or the log volume of functions at a distance epsilon away from fw, indicates how easy it is to obtain them. Now let me just explain what is the difference between the function space and parameter space. So parameter space, we can write loss or energy or whatever we want, and we have something like that, similar to all the pictures that everyone else drew. But what I'm actually interested in is saying we have a reference function, we allow it to have a certain level of error, and we are trying to find out how many such functions exist, because if there are many of them with low level of error, then the conjecture is that it will be easy to find one. Because we are never, ever really interested in finding the minimum. It is not realistic in any way. It somehow resonates with the two papers by Carlo Baldassi and Riccardo Cecchina. They are trying to guide the learning process towards areas with a lot of solutions that are not necessarily the minimum. So there is a combination of the entropy and the actual performance as part of the training method. Okay, so how do we do that? So we look at two systems. The reference function, fw hat, which is a number of layers connected by random variables, w, which we will take, random vectors that we will take from some distribution. And we have a perturbed function, fw, which is the same, except for the fact that the w's are perturbed to some extent in order to allow for some error and to check how many such functions exist. So we map this structure into a disordered system using generating functional analysis and analyze it. So each one of these elements is a discrete vector with plus minus 1. We can also accommodate any other activation function. So this is a sine function, but we can, again, I'll later on show you that also ReLU can be analyzed, for instance. So if we start with the same input, it will be modified differently throughout the layers. So the generating functional analysis and all of this stochastic dynamics of spin glass systems usually deals with time. We are going to convert time into layers. So the moving from one layer to the next is akin to changing a time step in the dynamical system. I should mention that there was somewhat similar work done on the basis of naive mean field theory by Poole and Ganguly and others. So how do we use stochastic dynamical systems? So for those of you who are not in the business of dynamical systems, we can think about the probability of the state of the system at layer L as being some probabilistic function of the parameters that are connecting layer S L minus 1 to L. In the following way, this is a very simple dynamics. You have an inverse temperature, which just tells you how strict you are in adopting this new state. So you have an exponential beta multiplied by the possible state of the system and the field that is induced by the previous layer. So the previous layer is a vector S hat L minus 1, me multiplied by W hat. divided by square root of n for scaling. And this simply gives you an exponent divided by the normalization factor for each one of the elements. We can do exactly the same thing for the perturbed system, and we move from one layer to the next in this way. In the limit of beta going to infinity, this will give you a deterministic rule, obviously, because the probability will simply take the higher value and nail it. So given this probability, we can always look at objectives objectives of interest, and the angled brackets simply mean that we are averaging over the entire trajectory. So if we want to, so this objective function is some function of the variables. If we want to sum over all of the variables, we have the initial condition, which is this for both systems, multiplied by the dynamics, and we do the averaging, and we get the value for the objective. For discrete spins, the overlap between the two systems is of interest because it tells you what is the difference or how aligned the two systems are. And this is denoted by q to the power of L. It also comes automatically out of the quenched averaging that I'm going to show you later on. So what is the generating function analysis scheme? So the idea is as follows. We can write e to the power of minus I, sum over the states of all of the variables in the two systems, multiplied by dummy variables psi and psi hat. If we manage to calculate that, deriving the moments, the various moments, is quite easy from here, because we can differentiate whatever we get here with respect to psi or psi hat, or both, and take them to 0 afterwards. So it will simply bring down from the exponent S or, so for instance, SL hat or S hat L SL, and we can calculate all of the moments that are of interest. So this is still for a system with given weights, given parameters. But normally in statistical physics, we are interested in ensembles. So we want to average over an ensemble of random parameters taken from some distribution, P of W hat, and also the perturbed system will have some sort of quenched variable attached to them. So this overbar represents an average of the generating functional over the possible parameters of the quenched variables. So after a long calculation, what we get is an integral of some order parameters, e to the power of n, some function of the order parameters. The order parameters come automatically from the averaging over W over the quenched variable of the system. And they represent over parameters, self-averaging variables that we will be able, that represent the state of the system. Yes, Mark?
Sorry, in your study, you want W to be a perturbation W hat, so
W, yeah.
That it's P of W condition W hat?
Yeah, so yes, so it is maybe misleading as it is written, but PW is delta W hat plus a perturbation. The reason I wrote it like that is because we have different types of perturbations, and as you will see in the next slide. But yes, you're right. So at the end of the day, we have something like that, and if we find the saddle point of psi, then we will find the dominant state of the system represented by the other parameters Q star, Q star, and then we know we can calculate a lot of things about the system.
So how do you treat this? It's just
what?
How do you go
from here to here? Right, so we do the quenched averaging. The quenched averaging usually locks the two variables, set of variables that are related to W, because the two systems are coupled by the set of parameters and the perturbed version. So it produces an average of S hat, for instance, which will give us Q, And the other Q will represent what? There are the cross of averages and averages of each one of the.
So you're saying, in fact, this thing is exactly a function, an integral on the overlap parameters, Q and Q hat, capital Q or whatever.
Yes. Yeah. Okay, so we replace the detailed representation of the system by a representation using only order parameters. And in this case, it is possible because it's a sequence of layers going from one layer to the next, so that they are in a way decoupled layer by layer. They are not, the layers are not coupled like in a recurrent network by the same set of variables. So back to this picture. So what we would like to do is to look at the expected error. So the error epsilon is just the Hamming distance between the two sets of, that's the way that we have defined it here, between the two values, end values of the vectors S and S hat at layer L, which is the end layer. So the expected value and quenched average value. So it can be translated to 1/2 of 1 minus QL, where Q is the overlap between the two S's. Is it clear? Good. And what we would like to do is to look at the entropy of FW at distance epsilon away from the reference function FW hat. Exactly this picture. So under the assumption that if we have many functions, if we increase the epsilon by a little bit, then it will be easier to find them. If we have just very few, it will be more difficult to find them. That's a conjecture, not proven at all. Okay, so let's first look at fully connected networks in two possible cases, continuous weights and binary weights. So the probability, we assume that all of these variables are IID from a Gaussian distribution of sigma squared, and we introduce a perturbation in order to generate an error, which is delta W. So W hat is taken from a Gaussian distribution, W without a hat is taken from W hat plus a perturbation eta, where delta W is just from a unit Gaussian. In the case of binary weights, we simply take each one of the variables to be either 1 or -1 with probability 1/2, and we will flip some of them in order to create noise in the binary case. We can calculate the overlaps from layer to layer, so QL at layer L will be related to the perturbation strength and to the values at the previous time. And in the case of the binary system, it will simply relate to the probability, flip probability P, and also the overlap at L-1. So the initial results that we got were that QL is decreasing, disappointingly, decreasing with layers. So we don't see that there is any contribution to correcting the values or strengthening, enhancing the overlap between the two systems. So on the face of it, the higher the perturbation is, the faster the decay is, but you are losing information and losing alignment because of the noise that appears in each one of the steps. And you can see in both cases, the binary and the continuous, this is the case. But I didn't talk about entropy yet, so let's see what we can make out of the entropic argument. So the perturbation of W is the introduction of a Gaussian variable with eta L coefficient. So the entropy is actually straightforward to calculate. In the continuous case, it's simply 1 over the number of layers, log of the perturbation in each one of the layers, sum over all of the layers. So it creates a shift in the weights from the reference point and simply represents some sort of a part of a sphere because of this perturbation. Similarly, in the binary weights, we have a simple entropic contribution due to the flip at each one of the layers, and we sum over the layers 1 over L. Okay, so far so good, but this is pretty simple because we have not talked about the different ways in which we can introduce these perturbations. We may want to introduce more perturbations in layer 1 and less in layer 2 and more in layer 3. So actually, this is not the question that we would like to answer. What we would like to do is to find the volume, we want to find the volume of functions that will be dominated by the optimal distribution of our budget of perturbations. So we have a budget of perturbations and we want to distribute it in such a way so that the error will be epsilon, but we will maximize the entropy. So eta L star is the set of arguments eta L that will maximize the entropy when we introduce them given a certain error epsilon. When we know that the error epsilon is defined by QL, at the end of the process, 1 minus 2 epsilon. Okay? So here we get quite interesting results because in both continuous and binary weights, what happens is that we prefer to give all of the perturbation budget initially to the largest layers. So this is layer 1, layer 2, layer 3, layer 4, and you can see that layer 1, we really don't want to touch. We touch it only if we really have to at 0.25, say, epsilon here. We start giving it some perturbations, but otherwise we spend all of our perturbations on higher layers. That means that the first layer is actually quite important in terms of reducing the error. In the binary case, it's even more striking because you first start with layer 4, you give as much perturbation as you can to layer 4, and only when you can't do any more, you start introducing perturbations to layer 3 and reduces the perturbation to layer 4 a bit, and so on and so on. And what also is interesting is that one of them is concave and one of them is convex, and it is particularly difficult computationally to find these results. So pictorially, if we have W1, W2, W3 to the different layers, when we are very close to the target, all of them are aligned in the same way. When we move a little bit away, layer 3 or 4, whatever we call it, we'll get more perturbations, and eventually if we go to epsilon equals 0.5, it really doesn't matter because it's random. Okay, all of that also was without examples because it was purely based on the topology and on the fact that we introduce random variables. So what happens when we introduce examples? So here we use an approximation, which is called the annealed approximation. And so let's look at the volume of functions with a certain error level. So this is represented by the top circles here. So when we introduce an example, and in the annealed approximation, we introduce them one by one, and each time we will simply fix 1 minus epsilon. We take all of this volume, and we fix one example which reduces, because epsilon is an error, and it will multiply it by 1 minus epsilon because we fix one of the examples not to have an error. And if we introduce p examples, we are left with omega alpha, which is omega 0, the overall volume, multiplied by 1 minus epsilon p. Another interesting thing to point out here is that this space will reduce very quickly because more of the higher error functions will be inconsistent with the new example that we introduce. all of the low error functions, probably many of them, will anyway agree with the result that we have. So this decreases relatively fast with the introduction of new examples. So we were very disappointed to find out that additional layers don't actually help. So just in order to explain the scaling, P is the number of examples, which is alpha a coefficient, multiplied by the number of free parameters, which is L, the number of layers, multiplied by n squared, free parameters in each one of the layers. And in order to find for any volume, what is the generalization error, we simply find the argmax epsilon of this volume, because it will dominate this volume. So when we plot the dominant error with respect to alpha, we see that L equals 2, L equals 3, and L equals 4 actually do not favor deep networks here in this particular example. And the decay is linear in time. So this was quite disappointing because we thought that the deep layer machines will have an impact on increasing or reducing the error as we increase the number of layers. Notice that this L2, L3, L4 refers to the whole network. It's not a running index. It's the number of layers that we have in the network. Okay, so this was all about densely connected systems. That means that there are all between two layers, all of the networks, all of the connections exist. Now I'm going to move to something else, which is called sparsely connected networks, which we have studied before, similar architecture. The only difference between this and the densely connected network is that between two layers, only k units are connected to the next layer. For simplicity, let's use W being 1, fix it to 1. And we've already studied this. It's a way of generating completely random functions. This structure, layer structure, is capable of creating uniform functions over the whole space of possible functions asymptotically. And it was actually introduced, the concept was introduced of noisy computation was introduced by von Neumann, who was wondering how comes that the brain, in spite of all of the noise that we have in the brain, still manages to calculate things. And in his mind, it was logical gates that are connected together. And he was wondering, can we structure somehow these logical gates in a way that will compensate for the noise? And apparently this is possible. So as I said, this is something that we've studied before, and we can also represent it as a recursive function of some order parameters. I'm not going to go through the calculation now. So just a very broad understanding of what does it mean, noisy computation. So you have a function represented by logical gates, and you introduce noise. When you introduce noise, the question is, what is the noise level above which there will be no resemblance between the function that you end up with and the function that you actually want to implement? So, and this is represented by this phase diagram. So up to a certain level of noise, if we start with magnetization 1 and completely arbitrary, and generalization error, which starts at 0, or generalization in this case, sorry, is the alignment between the two functions. At a certain point, the magnetization goes to 0, and the error becomes random. So we've used that also for these neural networks, because at the end of the day, the function that we used there was majority 3, which you can consider as a perceptron. It's a perceptron with a hard decision. Okay, so, and what I wanted to focus on is this hump. So the two values that are represented here, One is the magnetization, how biased the functions are, and we started with functions that are 1, 1, 1. And what is the error that is 1/2, 1 minus QL? What is the error that is observed at each layer? And this is for different noise levels. So the transition, the phase transition is at roughly at 0.15. So you can see that here, below this, this value, error value, everything converges to a high value of magnetization, and below it goes to 0. That means that it doesn't have any correlation with it. And similarly, the error up to 0.15 more or less, it will initially go up and then go down. So the argument is that in this case, actually it does favor deep networks. And the intuition is that if you start with some errors, they will be corrected by the majority function, because if you have relatively small number of errors, when you have majority 3, for instance, you will each time correct a few. So at the beginning, there will be high value, but slowly it will decay towards, asymptotically towards some error value. Okay, so all of that was about sine functions and about sigmoidal functions and things like that. Now let's look at the ReLU activation function. So in the case of the ReLU activation function, it's just 0 up to the value, the argument 0, and then linearly going up. So we do exactly the same thing. The only difference is that we cannot calculate, because it's not a binary value at the end layer, we cannot simply calculate the overlap. We have to subtract from the overlaps the means of the different values in order to get something sensible. So this is the similar value to the Q that we calculated before. So if you look at QL and a TROL, you can see that the ReLU function is much less sensitive to the noise, and it is remaining in a very positive value, both in the overlap and in the modified overlap ReL. So you can see that it is much less sensitive, and the reason for that is because it's a fairly simple function, so that in most of the range, the perturbations are not that significant. So the other thing that we wanted to look at is the influence of correlations. So we simply took Gaussian, the perturbations, sorry, the probability of the weights from Gaussian with some correlation matrix A, and we can see that there are negatively correlated and positively correlated weights. This is only for ReLU, and we measure again ReL as a function of L. What is interesting is that if the weights are positively correlated, there is much higher value and a lower expressivity of the ReLU network, while if you look at negatively correlated weights, they have relatively high expressivity. I should point out that this has been shown in numerical examples that people have looked at. Okay. The next thing that we've looked at is what is called convolutional neural networks. So in convolutional neural networks, you take a window and you connect elements from a window through a set of channels. So for instance, you take all of these guys and connect every 3 of them through some weights to a channel, and then you do what is called pooling. You collect together. There are different ways of doing pooling. There is average pooling and max pooling. You simply take the values of all of these variables. You take the maximum of them, or you take the average of them. Lots of heuristics. So we've implemented such a component in each one of the layers. This pooling reduces the number of variables in each layer by a factor of 2, so you have to take account of that. And what we focused on is the effect it has on the correlation between neighboring variables. And the reason for that is because convolutional neural networks works very well for images, for things that have some structure, spatial structure. So we wanted to look at the correlation between inputs and how they impact on the development of the functions. So we looked again at the overlap between the two functions, two types of functions, and they seem to, this is for ReLU and for sine function, everything seems to decay very quickly with respect to the number of layers, and in the case of ReLU, they decay much slower, and actually for small values, they hardly decay at all. That means that they preserve a lot of the information, and they also preserve a lot of the correlation, spatial correlation between sites. So I and j are indices at the input of two variables. The scaling of 2 to the power of L reflects the fact that with each layer, we are halving the number of variables, and therefore, in terms of spatial correlation, we have to take that into consideration. And it is interesting to find that the correlation is decaying very slowly with ReLU, very fast with a sine function. That may be the reason why ReLU is so useful for images and for things that have spatial correlations. Another thing that we looked at is sensitivity to the input values. So we take two systems. In this case, we do not perturb the values of the weights at all. We just perturb the values of the inputs, and we measure QL, the correlation between the end values of the variables with respect to the perturbation at level 0, layer 0. So in the sine function, it is very sensitive to perturbations. ReLU is not very sensitive to perturbations. So all of that was done for very large systems. And what we wanted to do now is to look at finite size effects and also to look at various types of perturbations. So what we use is what is called large deviation theory. And I'm just reminding you that in the generating functional analysis, what we wrote, we had a quenched average of an average over the whole trajectory of e to the power of I psi star s star plus psi dot s, which enabled us to get all of the moments. In large deviation analysis, what we are interested in is what is the probability of having a certain QL value, and we can write it again as the average over all of the trajectory, quenched average of delta QL minus SL dot SL hat divided by n. So we are looking at the probability of having different values of QL, not necessarily the mean values, the mean field values that we got before. In terms of the mechanism of the calculation, it is quite similar. We again do the quenched averaging and the thermal averaging, and we end up with some exponent that scales with n. So the value of this exponent in the extremum defines how fast this probability converges to a point. And how fast, when we go from the minimal value sideways, it will, the variable that we are looking at will increase. So phi q star k star, q star, q star, capital Q star, given QL will be the rate function for QL, will be the change for finite n of QL. And this is the result in the case of ReLU with 4 layers. So this is the mean field value. And as we move away from the mean field value, phi will get a value that is not 0, but some positive value. And that means that we will have an exponential decay depending on the system size. And these are obviously simulation results versus theory for n equals 64, n equals 128, just to validate that this is indeed correct. We use the same mechanism in order to look at two different cases, which is weight disconnection and weight discretization, or binarization and sparsification. And we tested them for both ReLU and sine, and it can be seen so that, so this is the sine function, this is a sine function, this is the ReLU, and this is the ReLU. That means that the value in terms of changes in Q are much, much smaller in the case of ReLU. Same here. So this is weight discretization. The consequences of these two is the fact that even if we discretize the weights, which saves a lot of computing time, or if we dilute the weights, which also saves a lot of time, we do not change the value of Q by much if we have more layers. Sorry, if we have less layers. Just to summarize, so I think that the main thing that I want to sell you is the framework, so that we can use generating functional analysis in order to understand better systems that are very difficult because they have so many different layers and recursive nonlinearity. We also saw that we have layer by layer matching of the weights, which we observe when we have getting closer to the reference function. So what happens is that you allow for big changes in the outer layers, smaller changes in the inner layers, close to the beginning, to the start. We also looked at correlated weights and convolutional neural networks, including ReLU, and finite size effects. So the caveat is that all of this is generic analysis and assumes random data and generic structure. It does not include the redundancy that we have in the data, the correlation within the data, the correlation within the architecture, and so on. Current and future work, so we are currently working on trying to understand the overall function space that is realized by feed-forward and recurrent networks for different activation functions, for sparse and dense connectivity. So one of the things that we've shown recently is that a recurrent network, if you have an activation function that is symmetric, a recurrent network has the same capability in terms of representing functions as a layered network with different weights at each one of the layers. So they have exactly the same range of functions that they can represent. Some of the future work that we want to look at is to look at overparameterization in the function landscape. And we want also to explore structured correlated inputs, so more or less along the lines of what Mark presented today, to try to find out how we can utilize the same kind of structure in order to analyze more realistic data. Another thing that we can do, we have not played with it at all, but is to optimize the variable hidden layer size, because all of these analyses accommodates different layer size. So we can attach a certain width for each one of the layers and find out how to optimize it or how to make the most of the deep layer network. And I think I'm done. Thank you.